Every person alive today, all 8 billion of us, may descend from just 1,280 humans who survived an apocalyptic climate disaster 900,000 years ago. Scientists discovered this by reading the ghost story written in our genes. This isn't some abstract calculation or theoretical model. In 2023, researchers applied a new genomic analysis technique called FitCol to the DNA of over 3,150 modern humans from across the globe. What they found defied belief, a signal so clear and so catastrophic that at first they thought their methodology must be flawed. Between 930,000 and 813,000 years ago, the human population crashed by 98.7%. From an estimated 100,000 individuals, our ancestors plummeted to around 1,280 humans, and they stayed at that impossible number for approximately 117,000 years. To put this in perspective, 1,280 breeding individuals is smaller than the population of many endangered species today. Mountain gorillas number around 1,000. Black rhinos hover near 5,000. Our ancestors maintained population levels that modern conservation biologists consider critically endangered for over 100 millennia. The discovery emerged from patterns hidden deep in our DNA. The FitCol technique traces coalescent patterns, essentially following genetic lineages backward through time until they converge. When populations are large, these lineages take longer to find common ancestors. When populations shrink, the coalescence accelerates. The signal from 900,000 years ago shows an extreme acceleration, a genetic traffic jam where nearly all lineages funnel through a tiny group of survivors. The timing of humanity's near extinction was no coincidence. Around 900,000 years ago, Earth's climate was undergoing one of the most dramatic transformations in its recent history. The Mid-Pleistocene Transition fundamentally rewired how ice ages worked, shifting the planet from relatively mild 40,000-year glacial cycles to brutal 100,000-year freezes that would dominate the next million years. The transition involved more than a temperature drop of a few degrees. The transition represented a complete reorganization of Earth's climate system. Ocean currents shifted. Atmospheric circulation patterns changed. The ice sheets that formed during glacial periods grew larger and lasted longer than ever before. Marine sediment cores from around the world preserved this transition in isotopic ratios, showing how global ice volume surged while temperatures plummeted. For a species that had evolved in the warm African tropics, this new climate regime was catastrophic. The worst phase hit around 875,000 years ago during marine isotope stage 22. Geological evidence from this period paints a picture of environmental collapse on a continental scale. In Africa, the cradle of humanity, forests retreated and deserts expanded. Rainfall patterns that had sustained ecosystems for millions of years simply failed. Lake levels dropped. Rivers ran dry. The Sahara, already a formidable barrier, expanded both north and south, swallowing grasslands that had supported diverse communities of plants and animals. But Africa wasn't the only continent in crisis. In Eurasia, where some early humans had already ventured, conditions were even worse. Ice sheets advanced from the north, in some places reaching as far south as modern-day London. Permafrost expanded across vast regions. The Tethys Ocean, which had moderated temperatures across southern Europe and Asia, was shrinking, eliminating a crucial source of atmospheric moisture. Mountain glaciers expanded in ranges from the Alps to the Himalayas, creating frozen barriers that fragmented habitats and populations. Climate models suggest that during the peak of marine isotope stage 22, average global temperatures were 6 to 8 degrees Celsius colder than today. But averages hide extremes. In continental interiors, winter temperatures might have plunged 15 to 20 degrees below modern levels. The stable, predictable seasons that humans had adapted to over hundreds of thousands of years became chaotic and hostile. The humans who lived through this bottleneck faced daily challenges that would seem insurmountable to us today. They had no fire, or at least, no reliable control of it. The earliest definitive evidence for controlled fire use appears at Gesher Benot Yaakov in Israel around 790,000 years ago, near the end of the Bottleneck period. Some possible traces of fire use exist from earlier times, perhaps back to 1,000,000 years ago at sites like Wonderwork Cave in South Africa, but these remain debated and likely represent opportunistic use of natural fires rather than the ability to create and maintain flames at will. Without fire, every aspect of survival became exponentially harder. Meat had to be consumed raw, limiting caloric extraction and increasing disease risk from parasites and bacteria. Plant foods that become digestible only through cooking remained inaccessible. The darkness of night left them vulnerable to predators. The cold of Ice Age winters penetrated without relief. Around 900,000 years ago at Happisburgh in England, humans survived winters in northern latitudes without fire or warm clothing, a feat that modern archaeologists describe with genuine amazement. The clothing situation was even more dire. The technology to create fitted garments wouldn't appear for another 850,000 years. Bone needles and awls, essential for sewing, don't show up in the archaeological record until around 45,000 years ago. The humans of the Bottleneck period might have draped animal hides over their shoulders or wrapped themselves in skins, but without the ability to create tailored clothing, such coverings would have provided minimal insulation. In freezing conditions, they were essentially naked. Their toolkit, while revolutionary compared to other animals, was primitive by later human standards. These ancestors used Oldowan choppers and early Aculin hand axes, essentially sharp rocks that required direct hand manipulation. They had no projectile weapons, no spears with stone points, no spear throwers to amplify force and distance, no bows and arrows. Hunting required getting dangerously close to prey, within arm's reach or at best a short lunge away. More often, they likely scavenged carcasses left by more efficient predators, competing with hyenas and vultures for scraps. The predators they faced were formidable. The Pleistocene world was populated by saber-toothed cats, giant hyenas, massive bears, and lions larger than any alive today. Without fire to keep predators at bay or sophisticated weapons for defense, human groups would have been vulnerable, especially at night or when defending carcasses. Humans often settled for leftovers after large predators ate, as indicated by cut marks on bones found beneath carnivore tooth marks. Their diet is glimpsed through coprolites, fossilized feces. When they could, they ate meat, as shown by bone fragments in human coprolites. But meat was unpredictable. Plant foods formed a crucial fallback, though the Ice Age climate made these scarce and seasonal. Tubers, nuts, fruits, and leaves that had sustained earlier populations became rare as forests retreated and grasslands desiccated. The small population size meant that humans probably existed in tiny bands of perhaps 20 to 30 individuals, scattered across vast distances. Finding mates outside one's immediate group would have been challenging, leading to inevitable inbreeding. Populations were extremely fragmented and isolated, as genetic patterns confirm. Yet somehow, despite all these challenges, they persisted. They found enough food to survive, enough shelter to endure the cold, enough luck to avoid predators, and enough resilience to continue reproducing even as their world collapsed around them. As Africa transformed into an increasingly hostile environment, something remarkable happened. Rather than simply dying out, some human groups attempted what must have seemed like an impossible gamble. They left. Around 900,000 years ago, human sites appear suddenly across Eurasia, indicating a migration wave that coincided precisely with the genetic bottleneck. This wasn't the first time humans had ventured out of Africa. Homo erectus had reached Asia as early as 1.8 million years ago, but those earlier dispersals had occurred during relatively favorable climatic conditions. The exodus of 900,000 years ago was migration born of desperation. As one research team noted, these humans packed up their lives and made long journeys into new environments, just as their homeland was becoming uninhabitable. Sea levels during glacial periods dropped by as much as 120 meters, exposing vast areas of continental shelf and creating land bridges where none exist today. The Red Sea, normally a formidable barrier, periodically became a narrow channel or series of salt lakes that could be crossed on foot. The Persian Gulf disappeared entirely, becoming a river valley. These temporary corridors offered escape routes from Africa, but they led to lands that were often just as challenging. Archaeological finds for this dispersal are scattered but compelling. At Atapuerca in Spain, Homo antecessor fossils date to around 800,000 years ago, representing one of the earliest known human populations in Western Europe. These might have been descendants of groups that fled Africa during the Bottleneck. At Happisburgh in England, footprints preserved in ancient mudflats show that humans had reached the extreme northwest of Europe by 900,000 years ago, surviving at latitudes where winter darkness lasts 16 hours and temperatures regularly dropped below freezing. Humans were present in China and Java during this period, though the fossil evidence remains frustratingly fragmentary. The pattern points to multiple small groups scattered across 3 continents, each finding their own refuge and way to survive. But these migrations weren't permanent solutions. The climate that drove humans from Africa was global. Glacial advances that turned Africa into a desert also buried northern Europe under ice sheets. Monsoon failures that dried African lakes also transformed Asian grasslands into cold steppes. The humans who fled Africa often found themselves jumping from one crisis to another. Some populations likely went extinct, leaving no descendants and only the faintest archaeological traces. Others may have survived in refugia, special pockets where local conditions remained more favorable. River valleys, coastal areas, and volcanic regions with hot springs might have provided microenvironments where small groups could persist even as surrounding regions became uninhabitable. The archaeological record from this period is so sparse that each new discovery can dramatically reshape our understanding of where humans survived and how they moved. Deep within the nucleus of every cell in your body lies a piece of evidence from this ancient catastrophe: chromosome 2. Humans have 23 pairs of chromosomes, while all other great apes have 24. This difference puzzled geneticists for decades until they discovered that human chromosome 2 is actually 2 ancestral ape chromosomes fused together. The fusion point is still visible in our DNA, marked by telomeric sequences, normally found only at chromosome ends, stuck right in the middle where the 2 ancient chromosomes joined. The timing of this fusion has long been debated, but the genetic bottleneck provides a compelling context. When populations are large, new chromosomal arrangements rarely spread through an entire species. The fusion would appear in one individual, be passed to some offspring, but would likely remain at low frequency or disappear entirely over time. But in a population of just 1,280 breeding individuals, genetic drift becomes powerful. A chromosomal change that appears in one individual has a reasonable chance of spreading through the entire population. The research team studying the bottleneck noted this connection explicitly. The chromosomal fusion might have first appeared during the bottleneck period, and because the population was so small, it eventually became fixed, present in every single human. Today, whether you're from Africa, Europe, Asia, Australia, or the Americas, you carry this fused chromosome. It's a molecular fossil of the bottleneck, proof that every human alive descended from the same tiny group of survivors. But chromosome 2 is just the most obvious genetic signature. The bottleneck left other marks throughout our genome. Genetic diversity in humans is remarkably low compared to other great apes. Chimpanzees, despite numbering only in the hundreds of thousands today, have greater genetic diversity than humans. Bonobos, with perhaps 20,000 individuals remaining, show more genetic variation than our species of 8 billion. This paradox makes sense only if humanity passed through an extreme bottleneck that eliminated most of our ancestral genetic variation. Around 813,000 years ago, something changed. Human numbers began a demographic recovery that increased 20-fold within a few thousand years. From 1,280 breeding individuals, the population grew to approximately 30,000. After 117,000 years of hovering at the edge of extinction, humanity suddenly began to thrive again. What triggered this dramatic reversal? The answer appears to lie in a combination of climate improvement and technological revolution. While ice ages continued their new 100,000-year rhythm, the particular severity that had characterized the bottleneck period eased. Rainfall patterns in Africa began to stabilize. Forests started to recover. Animal populations that had crashed during the crisis began to rebound, providing more reliable food sources for humans. But climate alone doesn't explain the rapid recovery. After all, conditions had fluctuated throughout the bottleneck period, with temporary warm phases that might have allowed population growth. The difference this time was that humans had acquired a transformative technology: controlled fire. At Gesher Benot Yaakov in Israel, archaeologists have uncovered definitive evidence of controlled fire use dating to 790,000 years ago. The site preserves traces of burning and clear evidence of hearths. controlled spaces where fires were repeatedly built and maintained. Charred wood, burnt flint artifacts, and thermally altered sediments show sustained, purposeful fire use. They could create fire when needed, maintain it over time, and employ it for multiple purposes. The impact of fire mastery cannot be overstated. Cooking became possible, dramatically increasing the caloric value of both meat and plant foods. Foods that were previously inedible or toxic became dietary staples. Parasites and bacteria that had plagued raw meat eaters were destroyed. The human gut could begin to shrink while the brain grew, as cooking essentially pre-digested food and reduced the energy needed for digestion. Fire provided warmth, extending the range of environments humans could inhabit. No longer confined to tropical and subtropical regions, they could survive winters in temperate zones. They could venture into mountains, across steppes, into forests previously too cold for a hairless ape. After 800,000 years ago, humans occupied higher latitudes and altitudes, territories that would have been uninhabitable without fire. Perhaps equally important, fire transformed the night from a time of terror to a time of opportunity. Predators that had stalked human camps were kept at bay by flames. The darkness that had confined activities to daylight hours was pushed back. Groups could gather around hearths, extending social time, sharing stories, planning hunts, teaching skills. Some anthropologists argue that fire was crucial for the development of language and culture, providing the extended face-to-face time necessary for complex social learning. Fire also revolutionized hunting and foraging. Landscapes could be deliberately burned to drive game, clear undergrowth, and encourage the growth of useful plants. Wooden spears could be hardened in flames, creating more effective weapons even without stone points. Torches allowed tracking wounded prey or gathering resources in low light. The controlled use of fire turned humans from reactive survivors into proactive ecosystem engineers. The demographic explosion that followed fire mastery was unprecedented in human prehistory. Within perhaps 10,000 years, a blink in evolutionary time, human populations recovered and exceeded their pre-bottleneck numbers. Populations expanded across Africa and into Eurasia, shifting from desperate refugees to successful colonizers, per genetic evidence. By 700,000 years ago, humans were established across the Old World, from South Africa to China, from Spain to Java. The bottleneck may have fundamentally transformed humanity, as well as nearly destroying it. From the tiny population that survived emerged something new, a lineage that would eventually produce Neanderthals, Denisovans, and modern humans. Some researchers argue that the extreme selective pressure of the bottleneck accelerated human evolution in ways that shaped our species' entire future. Could the bottleneck have catalyzed this transformation? The research team that discovered the genetic bottleneck explicitly raised this possibility, suggesting that natural selection during this period might have accelerated the evolution of the human brain. Any genetic variant that improved survival would spread rapidly through the entire population. Traits that might take millions of years to become fixed in a large population could become universal in thousands of years during a bottleneck. This speculation remains controversial. We cannot directly observe the brains or behaviors of humans from 900,000 years ago. The fossil record is too incomplete to track gradual changes in brain size or structure through the bottleneck period. The genetic evidence, while compelling for demographic history, cannot yet reveal specific adaptations that might have emerged. Some scientists, like Antonio Rosas of Spain's National Museum of Natural Sciences, caution against overinterpreting the bottleneck's evolutionary significance without more direct evidence. Yet the timing is suggestive. The last common ancestor of modern humans, Neanderthals, and Denisovans, based on genetic dating, lived approximately 600,000 to 700,000 years ago, shortly after the bottleneck ended. This ancestor, whether we call it Homo heidelbergensis or another name, appears to have been fundamentally different from earlier humans. Larger-brained, more technologically sophisticated, capable of surviving in a wider range of environments. The bottleneck may have been the crucible in which these new traits were forged. Even if the bottleneck didn't directly cause these evolutionary changes, it certainly shaped their context. The tiny population size would have allowed new mutations to spread more easily through genetic drift. The intense selection pressure would have rapidly eliminated deleterious variants while preserving beneficial ones. The geographic dispersal during and after the bottleneck would have created isolated populations where different evolutionary experiments could unfold. The modern human lineage, the Neanderthal lineage, and the Denisovan lineage all emerged from this post-bottleneck radiation, each adapting to different environments and challenges. Every human trait, from our unusual chromosome number to our complex brains, from our capacity for language to our tendency toward cooperation, may have been shaped by this ancient crisis. We are all descendants of the survivors, inheriting both their genetic legacy and the evolutionary innovations that allowed them to persist when extinction seemed certain. The next time you meet another person, anywhere in the world, remember that you're looking at a distant cousin, a fellow descendant of the same tiny group that nearly vanished 900,000 years ago. Our differences, profound as they may seem, are trivial compared to our shared inheritance from those who survived humanity's darkest hour. We exist because they endured. 8 billion lives trace back to 1,280 who refused to be the last.